This is the brief on geometric integrals and vector area. Vector calculus can be a real headache, but what we're looking at here is a great demonstration of Stokes' theorem that connects the abstract math to practical physics, making complex loop problems, well, a whole lot easier to solve. First, there's this really cool geometric shortcut. When you mathematically trace a path around a loop, the calculation isn't random at all. It actually simplifies down to exactly twice the vector area inside that loop. So does this hold up if the shape gets all twisted? For our second point, we applied this to a complex saddle-shaped loop, and despite the 3D complexity, symmetry meant we only had to look at the loop's flat shadow to get the answer. It just shows how robust this method is. Third, we moved beyond simple loops to see how they interact with a general vector field. When we applied this to a sort of swirling field, the math showed exactly how the surface's curve interacts with the local rotation, and it gave us a precise negative value, not some messy variable. And finally, we proved this works numerically. In a demo, we built a smooth loop out of little straight line segments, and as we added more and more pieces, the result got closer and closer to our theoretical ideal value of 2. A perfect convergence. This analysis really confirms that powerful link between theoretical vector area and what we actually see in numerical simulations. And that's how you turn tricky calculus into a truly reliable computational tool.